So in the past, when we've looked at a mirror, we've seen that the angle of incidence is going to equal that angle of reflection. So if we have a ray coming in, we're going to have a ray coming out, and these two angles, angle of incidence, is going to equal that angle of reflection. What we're going to do with optics is we're going to see how this now takes place, but we're not going to have a flat mirror. Instead, to start with, we're going to have a mirror that now has some curve to it. It's going to be concave. And if we're looking at the mirror on this side, this would be a concave mirror. If we were looking on this other side, this would be a convex mirror. And we're going to see how the light interacts when it strikes from either side of this mirror. Now, we're going to focus first on concave mirrors. And what we're going to see is that the different shape of concave mirrors, so all of these, if we're looking at them as light traveling in from the right-hand side, are going to be concave mirrors. And the different mirrors have different physical setups based upon what's called their center of curvature. So if we imagine this mirror continuing in its circle, the center of curvature would be the center of that circle that is taking place. So all these concave mirrors are simply some portion of a circle, and this right here, right, would be my center of curvature. The CFC, or the center of curvature. And then what we're going to look at is how does the differing shapes of these mirrors impact the image that we might see. So what happens with a concave mirror? Well, what we're going to do is we're going to imagine this concave mirror has this line, which is right at the center, and we're going to say that this is my center of curvature, right here, the CFC. And so that's the radius of that. Now, what we can have to understand is that as light travels in and hits the mirror, it's going to have a reflection. And similar to what we've talked about in the past, this angle here, the angle of incidence, has to equal that angle of reflection. Doesn't matter where that light strikes. It could strike here. It's going to have a perpendicular line, which is my normal, and I'm going to have a reflection. And again, this angle and this angle should be the same. So when we have light that's coming parallel from a long way away, it's going to strike the mirror and it's going to reflect back. And so what we're going to look at is what actually happens with that. Now, if a light was traveling along this principal axis here, it would reflect straight back. And so there's going to be some geometry rules that we're going to follow to help us understand the pattern that takes place for concave mirrors. Okay, so when we set this up, we're going to have our mirror here. We're going to have what's called the principal axis going through the center of their mirror. And then we're going to have our center of curvature marked here. And then this point is going to be called our focal point. And our focal point is going to equal 1/2 our center of curvature. And that is just what it always is. Now, as we set this up, we're going to have an object and an image indicated by an arrow. It's typically how we do it. So we're going to have an object, which is right here. That's our object indicated simply by an arrow. And we're going to draw 3 different beams of light coming from that object. All of them are going to come straight from the tip. The first one is going to move parallel to my principal axis. It's going to strike my mirror. And when it does that, it always comes back through my center of curvature. So that's line 1. My second line is going to be through my focal length. And then it's going to reflect back parallel to my principal axis, like so. That would be line number 2. So line 2 is through my focal length, then reflects parallel to my principal axis. My third line that I could draw is going to be straight through my center of curvature. And I could imagine this mirror, right, would extend here, And once it does, if I'm through my center of curvature, that is my radius. So my normal line is showing that this line is hitting perpendicular, so it's going to reflect straight back. So the arrow would be here and then straight back, and that would be line number 3. So my third rule is simply through my center of curvature, and it's going to reflect straight back. And what we're going to get is we're going to get a point where all 3 of these beams overlap, and that is where my image is going to be formed. Now this image is going to have some characteristics that we need to understand. The first one is that it is a real image. It's going to be able to be projected onto a screen. The second one is that it is smaller. It is smaller in terms of size than my object, and I can tell that this is 2 large squares up. This one is simply 1.5, so it's a smaller image. The third one is that the image is closer to the mirror than my object. It is closer to this point here than my object. And the last one is that it is inverted. So it is upside down compared to my object. The last part then is how can we put all of this information and this information into a mathematical relationship. And so what that's going to look like is that's going to look like 1 over f equals 1 over v plus 1 over u, where v is going to be this distance. Oopsie. V is going to be this length from the mirror to the image, and u is going to be this length here from the object to the mirror. So if I were to do this based on what we have here, if we just say each one of these little marks is going to be 1 centimeter, I would say 1 over f, which my focal length is going to be 1, 2, 3, 4. So that's 1 over 4 equals 1 over u, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1 over 10 plus 1 over u, which u here is 1, 2, 3, 4, 5, 6 and a half. And that mathematical relationship should hold true. And we can see that it does, because if we look at this, this is 0.25, this is 0.1, and this is 0.15. And those 3 added together are going to, or those 2 added together are going to give me the 0.25. So this is the equation then that I can use to relate the object, the image, and the focal length.